Hello everyone and welcome back to my channel Gyan Sampada. In our previous classes we were discussing about magnetic resonance phenomena, under which we had a detailed discussion upon spin lattice relaxation, and today we are going to deal with another type of relaxation phenomena, which is nothing but spin-spin relaxation. While understanding about the main criteria which differentiates between spin lattice and spin-spin relaxation, we had made use of the fluctuating field as well as the static field which is applied. And we know that for a spin-spin relaxation, H should be very much less than Hi, where H is the applied static field and Hi is the fluctuating internal fields produced by the dipoles. And from the heading we can understand here only the spin systems are involved and not lattice. So the main effect is to change the direction but not the magnitude of the field that each dipole is going to see. So in detail we have understood based on H and Hi, and today we are going to study it in more detail using some of the equations and mechanism. So let's start our today's class on spin-spin relaxation. Experimentally it is found that as frequency of oscillatory magnetic field, that is denoted as omega, as it increases, the absorption additional to the spin lattice absorption is occurring. That is, omega increases means absorption is also going to increase, because we have seen under magnetic resonance when we apply magnetic field which is static in nature, then precession of the moments takes place, whereas when we apply alternating field or oscillatory magnetic field also, then energy absorption is going to take place, and here omega is the frequency corresponding to the oscillatory magnetic field. And in our previous class we had seen the graph of susceptibility, under which we had also plotted a graph of energy absorption. So this graph, which is shown in dotted line with A, it represents the absorption of energy due to spin lattice relaxation, whereas A dash represents due to spin-spin relaxation. So here clearly we can observe from the graph, as the frequency increases, because along x-axis we have omega into tau 1. So tau 1 is spin lattice relaxation time, whereas omega is the frequency, and if we move from left to right, omega is going to increase, and as omega increases we can observe energy absorption is going to deviate from this graph. That is, at higher frequencies we observe certain extra amount of energy absorbed, which we call the energy absorption due to spin-spin relaxation. So this is as per the graphical representation, and in general we have energy absorbed per second per unit volume equation as A is equals to omega by 2 chi double prime h1 square. So all notations are having the standard meanings as per our previous classes, where chi double prime explains about the imaginary part of the susceptibility, h1 is the oscillatory magnetic field. Let us call it as equation number 1. And then if we substitute the contribution to chi double prime by the spin system, then we get the value for A prime, that is corresponding to the spin-spin relaxation. So when we do so, we can find that chi double prime due to spin system, that is due to spin-spin relaxation, will be equal to chi s omega tau 2 divided by 1 plus omega square tau 2 square, which we are calling it as equation number 2. So this chi double prime is similar to that of chi double prime which we have seen in spin lattice relaxation. The only difference is that in spin lattice relaxation we had tau 1 instead of tau 2, and instead of chi s we had chi t minus chi s. So tau 1, which was spin lattice relaxation time, is replaced by tau 2, which is spin-spin relaxation time, and chi t minus chi s, that is the additional susceptibility associated with spin lattice interaction, is replaced by chi s, that is susceptibility appropriate to only the spin system. So this represents the imaginary part chi double prime of spin-spin relaxation, which we are calling it as equation number 2. As we are mainly dealing with a paramagnetism, for paramagnetic relaxation studies, initial tail of the spin-spin absorption was studied initially, that is in this absorption graph. Therefore, we can say omega square tau 2 square is very much less than 1, because initial tail means at comparatively lower frequency. Therefore, now we can say equation 2 gets reduced to chi double prime of spin is equals to chi s omega tau 2 divided by 1, because the second part is very much less than 1, so it can be neglected. So it will be equal to chi s omega tau 2, which we call it as equation number 3. And thus our spin-spin absorption is given as A spin or A prime, however it is okay for you, will be equal to 1 by 2 as it is, omega as it is. Instead of chi double prime, we are substituting chi s omega tau 2. So omega into omega will become omega square into h1 square as it is. So just we have substituted the value of chi double prime in our equation number 1, so that we get spin-spin absorption, which we have called as equation number 4. And this is a very important equation when we consider spin-spin relaxation. But how to find it out? That is, measurement is important. How the measurements are done? So this equation was first determined by colorimetric measurements of absolute absorption, due to which this method is commonly restricted to the frequency range of 10 to 10 raised to 2 megacycle. Megacycle means 10 raised to 6 cycles, or if you consider 10 raised to 6 cycles per second, then it will be equal to 1 megahertz. So this is for the frequency range. So only when the frequency range lies in between these, then colorimetric measurements are fine. But if the frequency range is different, that is for the frequency range of 10 raised to 2 to 10 raised to 3 megacycles, then spin relaxation time can be determined by dispersion measurements, or that is by measuring the absorption as a function of frequency. So these are the two ways which are used for measurements, and we know that the spin-spin relaxation time is a measure of time required to establish the thermal equilibrium in the spin system. So whenever there is an oscillatory field imposed on a system, then the system is perturbed, means it is in the non-equilibrium state, and whenever it is in non-equilibrium state, it tries to come back to its equilibrium, and the time required for the spin systems to come back to its equilibrium is nothing but spin-spin relaxation time. But this is comparatively smaller when compared to spin lattice relaxation time, which we have already seen in our previous classes. So final destination is to attain equilibrium. So then moving to very important thing, which is the origin of tau 2, that is origin of spin-spin relaxation time. So origin of tau 2 on microscopic basis must be sought by considering different mechanisms by which spins are going to interact. So we are going to try for different possibilities for explaining the origin of tau 2. So if we consider the local or internal magnetic fields at a dipole which is produced by neighboring dipoles, then these neighbors will have their dipole moments arranged over a possible spatial orientations, and as the transitions between different energy levels occur, the arrangement is going to change. That is, the internal magnetic field will vary from dipole to dipole and also with respect to time at a given dipole. So these are the two parameters. And we know that the average of internal field is going to be 0. So how to find out the fluctuating internal field is the question. So whenever the average internal field is 0, we can calculate the RMS value of HI, that is root mean square value of HI, which will be equal to square root of 2 mu square summation over j of 1 by Rij raised to 6. So this is a standard equation where notations are having their usual meaning. So whether or not a static field is applied, dipole is going to precess with a range of frequencies. It is not going to be 100% at rest, because other factors are also going to act on the system, and this spread of frequencies will be given approximately as delta omega approximately equal to GE by 2mc into HI, where G is the splitting factor, E is the charge of the electron, M is the mass, C is the velocity of light. So if we just substitute the values and also substitute the value of HI by considering certain number of systems, then we find that the spread of frequencies comes off to the range of 10 raised to 10 per second. And if we know the frequency, we can find out the time, that is both are inversely proportional. So we can say that the relaxation time, which is tau 2, will be approximately equal to 1 by delta omega, which is approximately equal to 10 raised to minus 10 second. And this is the time that a dipole will require to reorient itself about a different precession axis, which is the significance of spin-spin relaxation time. That's why we say whenever H is very much less than HI, the dipoles are going to undergo slight reorientation and they will precess about a new field direction. And this is the time required to do so. So this is how the origin of tau 2 can be understood. Then moving to the nature of the field. So in the vicinity of imperfections, if the imperfections are present, then the crystalline field will be somewhat different from the other regions of the crystal due to the imperfections. So when there are imperfections, both zero energy level splitting and G value of the paramagnetic ion, which is located at or near the imperfection, will also be changed. So whenever imperfections are there, crystalline field changes, that is zero energy level splitting. It means that energy levels are going to split up even when we are not going to apply any field. So even when external field is 0, energy levels will split, and also G factor is going to change. Due to this, there will be a random variation in frequencies required for resonance, and thus the resonance lines will be broadened. And to understand this, we need to go for quantum mechanics, and according to Heisenberg uncertainty principle, we have delta E into delta T approximately equal to H cross, where we know energy and time are canonical conjugates. So delta E represents the spread of energy levels and delta T represents mean lifetime of the state. Thus, dispersion in precession frequencies will give rise to a broadening of systems energy levels of delta E is equals to or approximately equal to H cross into delta omega, because we know in general E is equals to H cross omega, and here we are representing with respect to broadening. So delta E, it corresponds to delta omega. So the spin system may be pictured as attaining thermodynamic equilibrium by small energy changes over energy range delta E. This is how we can interpret this equation. And then moving to the mechanism where we consider the phase destruction. So we may also consider these mechanisms as phase destruction processes. But why is the question. So for if two dipoles were, let us say, precessing in phase at a given instant of time, then we would expect them to lose this phase relationship in about time tau 2, which is spin-spin relaxation time. So as such, at equilibrium we can say different dipoles, or for example two dipoles are precessing in phase. But when the perturbation or the external fields are going to act, especially the oscillatory field, this phase relationship is disturbed, due to which we call that there is a phase destruction taking place. And if the dipoles were precessing about the field in z direction, then we can say that the phase destruction would occur for x and y component of magnetization, that is mx and my. And similarly in different direction, if precession is along x direction, then phase destruction will take place in y and z direction of magnetization, that is my and mz. So it is the perpendicular relationship. And to describe this phase destruction, Bloch had introduced the phenomenological equations, which are nothing but dmx by dt is equals to minus mx by tau 2 and dmy by dt is equals to minus my by tau 2. So these equations defining the spin-spin relaxation time have not been employed for interpretation of paramagnetic relaxation experiments, but widely are used in theory of paramagnetic resonance, both for electron dipoles and nuclear dipoles. So as these two equations were given by Bloch, these are called as Bloch equations. So it is something like rate of change of magnetization itself. So in the numerator we have magnetization term, in the denominator time. In the right side also we are having the similar nature only. So in detail we will use it in our line width correction. For the time being, these are the Bloch equations which describe the phase destruction in a system. So after considering all these things, now let us move on to the calculation. How to calculate tau 2? Bloch calculated the spin-spin relaxation time from absorption from theoretical considerations. And by his theoretical considerations, spin absorption is given by the equation A spin is equals to omega square h1 square by 8 kT. Summation runs over the range of energy levels of square of mod of expectation value of m, that is magnetization. So this is expression which is purely quantum mechanical, and if we use equation number 4 and 9, if we equate these two, because in both the equations LHS part is the same, that is absorption of energy due to spin-spin relaxation. So when we equate, we get the value for tau 2, which we have called it as equation number 10. And by applying certain boundary conditions and also some of the assumptions given by Bert Brower, we get tau 2 is equals to 1 by 8 pi into h divided by g mu b into hi. So when we use this equation, the order is the same which we have obtained from the previous equation, where tau 2 is approximately equal to 1 by delta omega, which is approximately equal to h by 2 pi g mu b into hi. So order remains the same, but they are going to just differ by small numerical factor. So the equation given by Brower is also valid. So this is how calculation of tau 2 can be done. So in our today's class, starting from what actually is spin-spin relaxation, we understood how to measure it, the nature, the expressions, the calculation part, the phase destruction term, and whatever important factors we should know when we are going to consider spin-spin relaxation time. So in our last two classes and today's class, we have completed with the relaxation phenomena, under which we have studied in detail about spin lattice relaxation and today about spin-spin relaxation. So this ends the topic of relaxation phenomena in magnetic resonance, and our next class will be based on the line widths, that is the correction factor to the basic principle of paramagnetic resonance. So whatever limitations we had in our previous class of deriving basic principle of paramagnetic resonance will be solved in our next class. Till then, study well, practice more, stay tuned, and thank you for watching.